Bio here. We are going to talk today a little bit about pressure units and Dalton's Law as we get into our new unit, which is directly related to gases. Now, gases play a very, very important role in our lives. You can think about the gas that we use to cook on a daily basis. You can think about the gases that are in the air that we breathe. But it's also very important in other realms of chemistry, such as manufacturing, natural gas, things like that. So we're going to dive into some of those ideas and talk about how we can deal with gas. In retrospect, I probably shouldn't have said how to deal with gas. That really sounds more like a personal problem. We're going to be dealing with gas in a chemistry perspective, not like gas. You take gas X for that. Anyways, your learning targets today, you should be able to explain the concept of pressure. I think there was a song like that. Under pressure, Okay, anyways. You should be able to convert between a variety of different units of pressure and understand and apply Dalton's Law of partial pressures. Our key vocabulary terms for today, we're going to talk about pressure. We also use the term Newton, millimeters of mercury. We'll discuss atmosphere, Pascal, and Dalton's Law of partial pressures. So when we talk about gases, the collisions of molecules in a gas create pressure. If you remember, gas molecules are very, very far apart, in particular when compared with solids and liquids. The more collisions that occur means that there's more pressure, and pressure is related to the amount of force that is produced per given area. So if a gas is compressed, we have a large number of gas molecules in a small number of area, the force is going to be higher, the area is less, therefore the pressure is greater. If we have a large room with not much gas in it, the area is large and the force is small, so the pressure is lower. If you want to think of another thing about pressure, think about when somebody steps on your foot. It happens to me all the time. If somebody steps on your foot in a tennis shoe, you definitely feel the pressure, but it probably doesn't hurt as bad. But if you've ever had somebody step on your foot in, say, maybe a high heel or something like that, somebody steps on your foot, that's really going to hurt because the heel, there's more force and a lower amount of area for that force to go, so the pressure is higher. Whereas in like a tennis shoe, the area is larger and the force is the same, so the pressure is less. As you see in the formula here, pressure is force over area. So the smaller amount of area that we have a certain force, the greater the pressure there is. Another example is when you take a balloon and let's say that balloon is filled with air and there's pressure that's exerted on the outside of the balloon. Well, when you take the balloon and you squeeze it, you're reducing the area. When you reduce the area, the pressure increases. And when the pressure increases, that balloon could potentially pop. So what are some units? How do we measure pressure? Well, the SI unit is the Newton. And the primary unit we use for gas pressure, though, is the atmosphere. So we probably won't use newtons a lot in this class. If you take a class of physics, you'll see a lot more with newtons. Some other units that we use are millimeters of mercury. We'll use the Pascal, the torr, and pounds per square inch. Probably one that we're most familiar with, PSI. You see that a lot with tire inflation and things like that. But as you see here on the right, there's quite a few different examples of units of pressure and what they equal. So 1 atmosphere is equal to 760 millimeters of mercury, 760 torr, 1.01325 times 10 to the 5th Pascal, and 14.7 psi. Since these units are equal to each other, we can use them in dimensional analysis. So let's go ahead and dive into this practice problem. It says, convert the average atmospheric pressure of Denver, Colorado, 0.840 atm into millimeters of mercury, torr, PA, and PSI. So we're starting with 0.840 atm, and the question is asking for us to convert to millimeters of mercury, torr, pascals, and PSI. So we're going to do 4 problems here, and these problems are all dimensional analysis. It's pretty straightforward how to do this. So let's start with the first one. We're going to start with 0.840 atm. Whatever unit is on top of the first step goes in the bottom of the next. So we have atm, and we want to get that into millimeters of mercury. And if you remember from our previous slide, 1 atm is 760 millimeters of mercury. We plug into our calculator and solve. Again, going back to some pretty simple dimensional analysis problems. Make sure we use the correct number of significant figures, which in this case is 3. We're going to have 638 millimeters of mercury. All right, pretty straightforward there. So also keep in mind for the second problem that torr is the same conversion factor. It's 760 torr per ATM. So the answer to the second one is going to be the same thing as the first one, 638 torr. Okay. We'll do the next one for PSI. So we'll have 0.840 ATM. Again, atmosphere goes in the bottom of the next step. We're going to convert that now to pascals. Pascals, 1.01325 times 10 to the fifth. And the same idea here. Plug into my calculator and solve. Make sure we use correct significant figures here. So what we end up with, 8.51 times 10 to the fourth Pascal. All right. And the last one is PSI. Again, same process, 8.40 ATM. 1 ATM on the bottom of the next step. It's 14.7 PSI. We do our math and solve. Using correct significant figures, we should get 12.3 PSI. Okay? So again, simple dimensional analysis to be able to convert between one unit of pressure and another. Dalton's law of partial pressures is pretty straightforward as well. Dalton's law simply states that the total pressure of the system is equal to the sum of all the pressures of all the gases in the system. So if you think about air, air is composed of mainly 5 different gases. We have mostly nitrogen. It's like 79%. Oxygen is around 16%. And then we have trace amounts of carbon dioxide, water vapor, argon, and so on. So there's a lot of different components that make up air. The individual pressures of all of the gases that are in air add up to equal the total pressure of air. So in order to perform these types of problems, you would simply be given either the partial pressures of the air, you would add them up, and that would be the total pressure, or you'd be given the total pressure and a couple of partial pressures with one left out, and then you would just solve for the unknown partial pressure. I'm not going to do a practice problem because I think it's pretty straightforward. So make sure to keep in mind that pressure is the relationship between force and area. When the area decreases, the pressure increases. And when the area increases, the pressure decreases. So they're inversely proportional. As one goes up, the other goes down. There are a variety of ways. There are a variety of different units of pressure that are used, and dimensional analysis can be used to convert between them. And Dalton's law of partial pressures states that the total pressure of a system is equal to the sum of the individual pressures of each gas in the system. System will be the word of the video today. I know it's a little bit late in the video. I try to keep them somewhere in the middle, but I'm an old man. I tend to forget things. At 33, things are getting a little tough. So system is the word of the video. Hopefully you understand the learning targets, and we'll get moving on with our next video here in just a little bit. Have a great day, guys. We will talk to you later. Bye-bye.